parallel RLC. At resonance, how it is behaving. If you have series RLC, if you apply some voltage here, the same voltage will appear across the resistor itself. Then what is happening to the inductor and capacitor? Okay, across the inductor, you will get plus JQV voltage. Across the capacitor, you will get minus JQV. Okay, V is the source voltage. That means you are getting some voltage that is equal and opposite. That means finally, if you consider both inductor and capacitor, what is the voltage there? That is like zero, because again, because any circuit that has to satisfy the KVL and the KCL. Okay, so in order to satisfy that, okay, the V is equal to V plus JQV minus JQV, again V is equal to V only. That means actually what is happening, okay, actually the inductor and the capacitor will be there. It is like, virtually it is like a short to us, because whatever voltage is there, same voltage is appearing here, then I can consider this as a short. Okay, that's why you can imagine like exactly at resonance, if it is series RLC circuit, you can consider like L and C is like a short circuit. Okay, you can replace, okay, mathematically circuit point of view, you can replace this L and C by short circuit, but it doesn't mean that practically this is short, but practically some voltage will be there. Okay, mathematically circuit point of view, you can consider as like a short circuit. Similarly here, once if you have a parallel RLC circuit, okay, see whatever this is like a total current, but exactly at resonance, whatever the current that you are having, the entire current flows through this resistance. Okay, and again here there is no current, but actually what is happening, there also current will be flowing across the inductor. Minus JQI current will flow across the capacitor, plus JQI current will flow. But once if you add this, that is like a 0 ampere. Okay, again, if it is 0 ampere, here also 0 ampere, it's like a open circuit. Okay, so that's why the entire current I is flowing into the R, because the current that flows here is like a 0 ampere. So again, for serious, you can, this will be useful. Okay, so now what is the answer for this one? Anybody? What is the answer of this network? Band pass, low pass, high pass, any answer? Yes. So see, at omega is equal to 0, at omega is equal to 0, when omega okay, now I need R2, this is R1. Okay, VA is the input voltage. Now you have to measure what is the output voltage. Okay, then voltage division you can apply. VI R2 divided by R1 plus R2. Okay, this is happening exactly at omega is equal to 0. Now what is happening at omega is equal to infinite? Because at infinite, the inductor will become open. Capacitor is like short circuit. Then the diagram comes like this. Okay. Again, here also no problem, because we are having some connection to the from input to the output. Okay, and again now also you can measure the output voltage with respect to input voltage VI. Okay, the output voltage VI is equal to VI again R2 divided by R1 plus R2. Okay, so what we are getting exactly at a 0 frequency or at a very high frequency, you are getting some value. But now what is happening at the middle? Okay, if middle frequency also allowing giving this value means again this is like an all pass filter, but you have to analyze. Okay, so what is happening at the middle, at some middle frequency? Okay, so at omega is equal to some middle. Okay, say for example that I can take like omega naught, some frequency. Okay, in the middle. Okay, suppose again when exactly when you are at resonant frequency. Okay, if you are at resonant frequency, what will happen to this combination? Okay, the parallel combination L and C is like an open circuit. Okay, just now we have seen, if you have a parallel combination at resonance, it is like a open circuit. Okay, so at resonance, okay, the parallel combination is like a open circuit. Now what will happen? Okay, so it is disconnected. Okay, it is disconnected. Then it goes like this. Okay, then this is plus, and then this is minus. This is V out, okay, V output, this is V input, this is R1, this is R2. Now you have a confusion whether you will get some voltage, output voltage due to this input voltage. Okay, again, you might have seen in some cases, even though the circuit is open, the voltage will be there because current is not there, but the voltage may be there or may not be there, but it all depends on where you are measuring the voltage. Okay, and again, you know one thing, whenever you have an open circuit, okay, without any confusion, you can take current as 0 there. Okay, current as 0 there. And again, you do not know what is the voltage here. Okay, I put this as an open circuit voltage. This voltage could be anything. Now you apply the KVL in this loop because this current is 0. And again, here also the same current will flow. The current is 0 only. Okay, because the current has to be same in the loop. Okay, now as it is open, the current is 0. You apply the KVL now. Okay, minus VI Ri R1 into 0. Now this is VOC, open circuit voltage, and again this is 0 into R2, okay, is equal to 0. So from this, what you are getting finally, you will get VOC is equal to VI. Okay, VOC is equal to VI. Again, from this, it's very clear what is your V0. Your V0 is 0 into R2 is always 0. Okay, so exactly at this condition, you are not getting any output, but where this voltage is going, this voltage drop will appear across here. Okay, again, you may have a doubt because you are having source voltage, VA is appearing across this one, then what will be the value here? It has to be 0 only. So somehow the voltage is there, but it is not there in the required point. Okay, you need the voltage here because here only you are observing the voltage. You are not observing the output voltage here, but you are observing here. But here the voltage is 0. Okay, so exactly at some frequency you are not getting anything. At low frequency you are getting something. At high frequency you are getting something. But exactly at a middle frequency you are not getting anything. So that's why that kind of filter is called a band stop filter. Okay, this filter nature is called a band stop filter. Okay, so the nature of the filter is band stop filter. Okay, like this you can take different combination and then you can analyze. Say for example, again you can take a resistance like this, capacitance like this, then you measure the voltage here. Okay, you give the input here, then what is the filter nature? Or you connect the capacitance here, you connect the resistance here, you give the input, then you measure the voltage here, then again this will give some nature. Okay, either like a one may be the low pass filter and another one may be the high pass filter. Okay, so you'll get the answer like this. Okay, or otherwise you can also do like this. You take the combination like this, and again here combination like this. Okay, now you may get some nature. Okay, so like this you try to analyze the circuit. Okay, at least you analyze the nature of this one because this was famous one, very basic circuit. Okay, this is a very basic format for low pass and a high pass filter. But again, even with the second order also you can design low pass and high pass filter, but this is like a first order low pass or high pass filter nature. Okay, so next we'll see Q factor of different element. Okay, element, and then what is the Q factor, quality factor of the circuit. Okay, so say for example, if you are having only resistance, okay, if you are having only resistance, what is the Q factor? The Q factor is 0 because when it is only resistance, you cannot store any energy because by formula, what is the formula of Q factor? The energy stored or power stored divided by power dissipated. So you cannot store any energy with the resistance. So Q factor is 0. And if you have only inductor value, if you have only inductance, pure inductance without any resistance, when you have a pure inductance, you can store the energy, but you cannot dissipate the energy. Okay, so energy storage is there, but there is no energy dissipation. It is like infinite because what is the Q means? Q means power stored divided by power dissipated, power stored divided by power dissipated. Okay, like again this is 0, this is infinite. Similarly, once if you have a capacitance, again here also you cannot dissipate any power, then again Q factor is infinite. Q factor is infinite. But once if you go to other combination, RL series element Q factor, if you take RL series combination, okay, or L series combination. Once if you have this combination R and L, and again Q factor is omega L divided by R. Okay, if you have R and C like this, RC combination, RC series combination, 1 divided by omega RC, and if you have like this RLC, again the Q factor is, we have calculated for series RLC, the Q factor is 1 by R square root of L by C, 1 by R square root of L by C. And then you just think it of, can we have without R, okay, without R can we have L and C in series? Okay, is it possible? Just to think over it. Okay, so with R is equal to 0, can we have this combination? If R is equal to 0, L and C means in series. Okay, if that is the case, Q will become like infinite. But just think over it whether that combination is possible or not in general. Okay, then the another combination is RL parallel. Okay, so this is L and this is RL parallel. Again, if RL parallel combination means R divided by omega L, just opposite. Okay, so previously in the series omega L divided by R. Now whenever it is in parallel, then that is like R divided by omega L. And RC parallel. Okay, RC parallel means what is the Q factor? It is simply omega RC, because when you have a RC in series, okay, R and C in series, you got 1 by omega RC. So once if it is in parallel, then simply omega RC. And again, this is like RLC in parallel. Okay, once if RLC is in parallel, then again just opposite to this one. Okay, whenever you have a series, Q is equal to 1 by R square root of LC, just opposite of this one, and that is Q is equal to R C by L. Okay, so anyway we have derived this. Okay, because somehow we have derived Q factor of series and parallel RLC, but from the basics of this one, then you just try to derive. Okay, how this is possible. Okay, when you have a parallel combination, how R by omega L is possible? When you have a series combination, how omega RC is possible? Okay, so what is the formula? I told you the formula is power stored. Okay, power stored divided by power dissipated. That is a formula for Q. Okay, that is a formula. What is the power stored? Okay, the power will be stored across the capacitor, but the power will be dissipated across the resistance. Okay, some voltage will be there across this. Finally, some power again in one cycle. Okay, in one cycle. Okay, what is the power stored in one cycle? What is the power dissipated in one cycle? Then you just try to prove this. Okay. Oh, so yes. Okay, so with this this topic is over. Next, we have to start the magnetic circuits. Okay, so I'll start on tomorrow.